So for the after every member of the breakouts has presented, there was supposed to be some summarizing discussion among the breakout leaders and everybody here. We're a little bit short of time, so it would be a 5-minute discussion. So if you guys want to try it, otherwise we'll just proceed with the next item on the schedule. And for the next breakout, you'll all be more seasoned with the mechanics, so I'm hoping that we can make the timing work a little bit better so that we can have a final panel discussion.
So there were a couple of things mentioned, and I was wondering if the groups could perhaps address it. One was there was a need to whether look at theory ahead of experiments or for primers or primers on information theory. I'm wondering about the converse. Do you guys feel like those that are working in information theory and biology have a significant or a sufficient appreciation for the biological challenges or even for the biology? And if yes, great. If not, are there ideas in terms of how to address that? And then the second question I have, if I can go ahead and put that forth. So there was also this issue of time and scale. One of the things that are attractive about information theory is perhaps the fact that it could potentially be scale invariant. So I'm wondering how that squares with we need to perhaps develop scale-specific models versus, is there an attraction for information theory to kind of span these scales?
So anybody can jump in, breakout leaders or anybody from the audience.
The first point that Group 1 made about each model system requiring its own version of the ITCC, ICCT, CI, whatever that model that we've been talking about. The point, to answer your first question, is that if you want to support collaboration across the two communities, there isn't one primer that the engineers and mathematicians need. The system that they're going to work on, they need to immerse themselves and learn it really well, and they need a primer specific to that particular system, and the details that they need will be different than the details somebody else needs. So in terms of thinking as a funding agency, enriching or expanding support for collaboration, for travel, for people with large teaching loads in mathematics departments, say, to have time off to spend time in the laboratories of potential collaborators, creative ways of fostering that interaction rather than trying to write a primer that you can distribute to everybody, because everybody needs a different one.
Yeah, along those lines, I was thinking about Nimbus or Nimbios and how they operate, setting up these little travel grants that you can get everybody to Knoxville and try to at least get up to speed experimentalists and something like that. Peter?
Yes. I want just to point out one thing, that semantics was mentioned in many of the concepts or sign and meaning and things like that. And I just have here the report of the NSF workshop from 2008, also on molecular communication and thing, organized by, I think, Suda and Nakano. And I looked at the report, and there was not a single mentioning of semantics in the whole 18-page something report, just as mentioning. So that seems to be really something new now.
Is this working? Yeah, it's working. Only a remark regarding collaboration between, say, engineers, computer scientists, and the like, on one side, and biologists on the other side. My experience is it needs a very tight cooperation at the beginning, at least, to learn from each other, to adjust the vocabulary, to really be able to talk. And it needs also, for us, like myself as an engineer or like, you need to offer some time to read biology papers beforehand, to get used to the way things are described, and get used to the environment. Later it is not so important anymore. So when it comes to travel, I mean, the US has actually an advantage because contracts of professors are usually 9 months, and you have 3 months time to do something else, which can be more easily used to do that. In Germany, this is not the case. So I had the advantage that I had a life scientist with the same interest very close by, so you could meet anytime. And we had a coupling element, which was a postdoc that was actually a bioscientist or bioinformatics guy, so he would understand both sides. This constellation is almost ideal, but you need to really have this chance to collaborate almost, not daily, but at least weekly.
If I may add to that, one thing that needs to happen in this initial collaboration is to set the expectations, right? So because a biologist might think that a modeler can solve everything, and a modeler can think that in 2 weeks you'll get results for some experiment, and none of those assumptions is true. Eric.
So I would say that one thing regarding this conversation between people who are sort of trained in different fields, I think one really serious problem is a lack of appreciation for sort of theoretical progress sometimes in certain communities within biology. So in our group, we talked about the need for, sort of being able to kind of, not necessarily make a prediction, but like to develop some sort of theory that isn't actually necessarily even about data, that's about how we think about the world. And I think that a greater appreciation for that among everybody would be super helpful. As for scale invariance, I just make a quick comment that I think, the point is that even if we get rid of all these issues about dynamics and all of this stuff, the scale invariance helps you in that you can apply a certain mathematical framework to multiple different things. But unfortunately, since we now agree, unlike the last time, that semantics is an issue, how we interpret the results, how we use that to inform our understanding of the biology may be very specific to the scale that we're talking about. So that's anyway.
Maybe to just add a couple of points. One is, I think there is a continuous maturing of biology, let's say, and the level at which the things are discussed. So at least what we've seen is that there were models perhaps 10 years ago that would be very suitable, even though they were incredibly naive. Now, both in experiments and in our understanding of the system, there's really a huge degree of maturing that needs to be followed kind of across the scale if you are hoping that the models will be taken seriously by the experimental community. And so the best way, I agree completely, is to really figure out a way to be not just to read textbooks or some basic reviews, but really be embedded, so you get a lot of the backstory, so to speak, and a lot of the information that may not be easily available. In terms of the scales, I think different things can happen on different scales. I'm not sure it's completely sort of easy to cut across. And you can think even in relatively simple ideas of signaling communication between the cells or within a cell. There could be a scale at which the signal changes. It will be the scale at which the system may adapt to the signal. It will be a scale at which, I'm talking about temporal scales, that different events like memory may be developing and so on. So it's actually a very good question of how much of that is going to be based on what you see in biology all the time, this separation of scales, and how much of that might be needed. I think it's a good question rather than a statement here.
So just to emphasize those points, in terms of collaborating, and do we know enough about the biology, I think it's really crucial to collaborate with biologists, but not just to understand the concepts, but maybe to collaborate around a precise biological question that can be tested in the wet lab, because the biologist may not be able to conceptualize their problem correctly and may not be able to communicate to you what the nature of the issue is. So if you have actually a direct experimental system, maybe between yourself and the biologist, you can actually model it better in ways that the biologist themselves could not. So it's also very nice because then whatever theory you have might be directly testable. So it's not just like a set of equations, and it's really you understand the strengths and limitations of your system. And then the second thing is that in terms of scales, we want eventually to have theories which are multi-scale, but if you do it right at one scale, then you can test the power of the theory to see if it will naturally go off to other scales. So it's hard enough to do it at one scale. Try to do it as well as you can in this one experimental system. And if by chance you actually see that this can scale up or scale down, then you have actually immediate validation that you've got something more powerful. So trying immediately to abstract things to solve the entire problem is just maybe too hard. Just doing one thing, one small thing right would be fantastic in the context of coding theory, in the context of information theory. So I think we need to be very modest about what we do know and just start with little steps, but with milestones. Yeah.
So I think we should wrap it up here and move on with the next session. So